one word of warning. That is something that I should not see, right?
Stay room.
Ah, that's what. Yes, rozumiem. Thank you for the introduction and for the possibility of being here. This is really a pleasure in such a nice place and to talk to people here. And yes, this is a word of warning at the beginning. This is an ongoing. And my talk will be divided into two pieces. The first one is about TTbar deformation, which I'm not an expert on. So it means there may be mistakes. And the second part is on the ongoing research, and it means there will be mistakes. Okay, so if you can live with that, this one. So I have decided to divide the talk. Yes. But first, I'm going to talk about TTbar deformation. One is the thing which people consider to be interesting. Then the classical TTbar deformation, some new stuff that appeared a little more than a year ago. And then the quantum TTbar deformation, a work that we are currently pursuing together in Rikard. And so far we haven't punched onto any nonsense stupidity, so we hope there will be some interesting things that come out of this process. So let me start with the TTbar deformation kind of motivation. So the first, I would say, problem and one thing, this is a bit based on something that Rikard should recognize, because I had the pleasure to listen to his talk several years ago, when he was talking about TTbar deformation. So the first thing was about the composition of TTbar. Not by TTbar, but in fact, when you consider not conformal but general two-dimensional theory, they have more components with stress tensor. They are not holomorphic, and there is no guarantee that if you take a product of two such components, that it will be well defined in coinciding points. Typically, there will be singularities, but the observations are much towards that if you form a specific combination of those, then the limit of coinciding point actually exists. And if this is so, it means that the correlation functions factorizes onto correlation functions of the components. Okay, that's why we stress that. And this was proven quite under quite a weak assumptions. It holds in rather general two-dimensional conformal field theory. What one means by such deformation, this is the formula I think most of you not only have already seen. So you take, say, some two-dimensional theory, you compute in this theory components of stress energy tensor, then you form such an operator. This is essentially a determinant of the stress energy tensor, and you deform your theory by adding to the actual integral of this determinant calculated at the current theory. Such a deformation defines for you a new theory. In this new theory, you compute new stress tensor, and in the next step, you add the deformation composed with this from this new one, stress energy tensor. So step by step, in each step having new objects, which is deforming your original theory. This is quite a formal expression, I would say, in most situations. So more specific, you expect that the deformation of any correlation function in the theory will be given by the correlation functions of the initial fields together with the deformed. This is a general setup if you do for instance. Okay? And here you have connected components. Good, so far so good. And now kind of general propaganda about this. So in certain sense, this deformation is solvable. You can compute many things in the deformed theory. Then you can deform essentially arbitrary two-dimensional local quantum field theory, so it's universal deformation. And even if you introduce by this deformation a length scale to the theory, it might not have one initially. It might have been CFT without such a scale, and you introduce just because if you compute the dimension of the TTbar operator, it is dimensionless, even if you integrate it, still so to make it dimensionless, you need to have a scale. But still, this theory, even if non-local for small distances, at least people think it should be non-local for small distances, it seems to be working. So,
And what's your definition of non-local then?
what's my
What's your definition of non-local? Which definition of non-local do you use?
And this is a kind of, I don't think I can really describe this. Well, you know what is local theory, right?
Okay, so what's the definition of local?
So what I would say, if I got here the local theory, I can define a set of local fields which describes for the theory, which, for instance, form representations in the Lorentz groups. Okay, and I can form, for instance, an action.
Okay, yeah. So we don't assume any Lagrangian formulation, or
there is some, and for instance, in the I would call it a local theory when in the Lagrangian you have only a finite number of derivatives, right?
Right.
You can have some more complicated formulae. Yes.
But that's not the definition you're using for non-local. Are you talking about the commutator of spatial?
Please let me refer to the first word that I said when I was showing the transparency as kind of propaganda. Okay. This is not the point I'm going to be really interested in. And moreover, there will be one standard example, which you probably know how to deform the single scalar theory, where you will see the resulting action, which is still it's a local but quite complicated area. Okay. And I'm not in the position to discuss this particular issue of being local or non-local. This is a kind of general statement that was introduced automatically. The theory that something non-trivial, complicated may happen at the distance between us. Okay. And I'm not prepared, not ready to discuss this in any detail. Good. So proceed, and then this is the standard classical example. What happens if you deform a single massless non-interacting scalar? This can be solved by a clever choice of an results. So you assume that even after the deformation, Lagrangian depends only on the scalar composed from a scalar field. Okay, and then first of all, if you assume that you have such a dependence in this deforming parameter in U, then of course I can compute the derivative of such a Lagrangian with respect to U. And on the other hand, we have already defined our variation, our deformation as adding the action, and this means also to the Lagrangian a product of the components of stress energy tensor. So if I have Lagrange being function of this type, so I can compute the components of the stress energy tensor with this Lagrangian for any f, and then can I add the determinant of the stress energy tensor. This is one my variation, so I can compute in another way derivative of my deformed action with respect to U. This time taking into account that I know how I change my Lagrangian. Okay? So we have these two ways of computing this derivative, and the resulting equation, or again y, it was on the previous transparency, is this combination. Mu times d mu phi d mu phi, so I can, using this identity, obtain the differential equation of this function F, solve it, and what we get here can be interpreted as a number of action for string in 3 dimensions in some specific dimensions. Okay, so this is an illustration how this deformation will work in some simple things. And I think quite nice explanation of the remarkable properties of the deformation, why it is so interesting. One of it can go and can be seen by considering a path integral deformation, the path integral derivation of the action of such deformation. And the effect turns out to be described by some action, which is in fact integral of some total derivatives, so can be deformed, can be integrated to the boundary. This is, and finally, let me offer you some more explanation. So this is the operator we want to plot our theory in the exponential. So the path integral, of course, it will appear in the exponential and the factor of I, or lack of the factor of I is essential, of course. So you can see that by integrating in the H in 2 dimensions, of course, the determinant is a quadratic function. So this is a quadratic integral, you can do it, and the negative measure, which we anyway do not depend on speed, neglecting the measure, you can get the left-hand side of the right. Okay. Now, if you have any local field and you write down explicitly the metric in the action, as you know, you can obtain the stress energy tensor by varying the action with respect to the metric. Okay, so this one can in fact be obtained as a result of infinitesimal deformation of the metric. You go from the flat metric, curved metric, and in the first order of the deformation, you obtain. So that's one deformation. Next, you have to, if you are in 2 dimensions, that any symmetric tensor can be written. Okay? And moreover, here, after some more, you can see that from the fact that this metric is coupled here to the conserved energy momentum tensor, then in fact you can show that this term, the scaling part of the metric, can also be written as it satisfies this equation, so it can be written as the sum of in complex coordinates it would be a holomorphic, anti-holomorphic part. Anyway, this term can also be written as a derivative of some scalar functions, so ultimately considered as a redefinition of the scale parameters alpha. And what you get, from proceeding in this way, that the action, this part of the action can be ultimately written as an integral just over the boundary of your space-time manifold. Yes?
All right. So the phi can be thought as a gauge field, right?
I mean, as an effect of reparametrization. Okay. You can consider reparametrization as a gauge symmetry, but it is very important you just do not have such a term in your H, because in the present situation, you can choose alpha in such a way that you use the required for it. And this is thanks to the fact that the here coupled to the other components drops out. Okay. And then the action you have really can be written as a boundary term. So if you have a trivial space-time manifold that you do not obtain anything interesting, there is also some constraint which those will be defined that we will discuss this in detail. Let me only mention that, so as you see, we have created this TTbar deformation for some change of metric. given by these alphas, and the boundary action containing this alpha. Okay, and from this, in some simple geometries, one can derive quite a simple equation. Let's count it. For instance, if you consider your theory to be defined as a cylinder, okay, you have some boundaries, some velocities, then, and if you define a ratio of the partition function of the cylinder, one of the leg precisely to the circumference, then it turns out that this function satisfies such a simple linear relation. If you consider a theory on toes, toes, come on, yes, thank you, this is toes. Let's see the toes. I like it. Look this way. Yeah. Yeah. So the totals, you can get quite simple differential equation. You now discover Z is partition function divided by the area, and I'm not going to show you any details of it. But for instance, as I said, again, I assume that some of them might have seen it, and those who haven't, well, it's not really a point to give all the details of the relation. But I thought it's worth noticing. For instance, if we are listening there, then you can expand the partition function in terms of such a form, and then you can show from the linear equation that the variation derivative of the energies of the subsequent levels in respect to these informal parameters can be presented in such a way that this is a momentum density. This equation was also derived by Zamolodchikov in the operator formalism. In this one, of course, I spared you details, but it would take, I think, like 20 minutes to show all the details, and the ratio is not that different. Okay? So, secondly, you can draw an exact consequences of this deformation, for instance, in the form of such a flow and the energies of the states in the theory. Okay, this is one of the particular reasons why people are interested in that. Then there are many other things people discuss, including, for instance, the holographic description of this theory, adding other deformations like with some currents that are present in the theory. There are conferences which discuss the TTbar deformation. So this was considered to be quite interesting. Okay, and now let me come to the main part of my talk. Please let me know what is the habit here, 60 minutes or 45 minutes?
So usually like one hour.
Up to 60 minutes.
Yeah, you can make it longer, it's okay.
I'm not going to. But sometimes in 45 minutes. So now, so let us.
This are even that's Zumba.
Just a mouse.
Thank you.
Move your slides by one.
So this is the word that was on the outline generating here. And the clever people who with them here asked several questions. So the following question. Okay. The TTbar operator is the term. It's a well-defined operator, but it has conformal dimension. So it's irrelevant. Theory, it really, if you start from any conformal theory, it will deform it, it will take it outside of the conformal point. But if we take experimental such an operator, it will be of conformal dimension 2. So formally it's not. So let's think what may happen if we consider a deformation like such. Okay? It looks ugly. It is ugly, but it's something actually done. And those gentlemen considered Lagrangian of the following form quite general. You have scalar fields, you have B field, you have some metric on your field manifold, model, very field. algebraic potential. And what happens if we deform such a theory in the R root TTbar operator? Okay. Then again, they had an argument. One can accept the arguments. It's not stupid. You can make two obvious invariants with respect to both any internal symmetry the metric on the manifold we have, and of course the two-dimensional such invariants with 2 and 4 derivatives. And since the two-dimensional metric has only 3 independent degrees of freedom, if you think of any invariant containing a larger number of derivatives and still being scalar, that it can be constructed as just a function of this. Okay, this is okay. And then they checked by solving this equation. You differentiate the Lagrangian with respect to the deformation, deforming the operator, and assuming the answer such that Lagrangian can be written as a function of x naught, or x naught can be something which does not depend on the two-dimensional metric. In particular, if we have such an action that this term is metric independent, right? It's because the contraction itself is two-dimensional epsilon. And when I took a more careful look at their paper, I was not quite sure how they want to include the two-dimensional volume. I assume it was a volume, but there may be some minor point to the start. But if we translate, they say, okay, we separate our theory into terms of two-independent matrix. So here, for instance, the B term together, derivatives, potential, which also do not depend on metric. And let us assume that our Lagrangian depends on those quantities together with x1, x2. And then you can see from this equation deformed by operator R that x0 is as undeformed in the flow, while x1 and x2 satisfy these relations. Quite nice, right? For instance, there are some details of how you can derive this quantity that I gave you before. And in particular, which I think could have been expected from the fact that this operator is marginal. If the trace on the undeformed energy momentum and stress tensor is 0, then the deformation preserves this fact. So it would be like a classical proof for this model that once you started from the conformal model, you stay within the space of conformal. Now, the simplest in that almost trivial with respect situation appears we just have a single massless scalar. You have seen that in such a case, the TTbar deformation leads to quite an interesting thing. Here, on the other hand, it's not the case. If your Lagrangian is just d bar phi in complex coordinates, then T is a d squared. We are on the classical level, so there are no ambiguities in the final form. And if I assign the points, then I believe these equations are obvious. TTbar is then Lagrangian squared, so the root is something like that. So for this theory, deformed by the operator R is just equivalent to change of the coefficient in front of the direction. Okay, seemingly trivial, but not quite. And let me stress, this is only a classical effect. Right? For the quantum theory, of course, is visible to me. This is not the correct definition of conditional intensity. We have a singularity of cosine points, so we would have to subtract the singularity before going to the mean. Yes, at the quantum level, life is more interesting. Okay, so let us discuss classical field at the quantum level in some more detail before the thing. So you can check if you do careful calculation, and hopefully without making mistakes, that if you have the coefficient g in front of the action, well, the coefficient g impacts the way the field is related to the momentum. And since you need the commutation of the canonical and conjugated momentum and the field are just proportional to the delta, so you get some relations between different objects, and in particular, if I want to write them in terms of canonically normalized oscillators, then there is some coefficient relation. And then if you have a coefficient of action, then you need to include properly this coefficient when you compute for the field energy momentum tensor. So things do depend on this G. In particular, if you have the energy momentum tensor, you can construct this is a simple exercise, but I mean, sometimes it's worth being aware. Even seemingly innocent coefficient of final action may have some. So you can compute with the ordinary CFD machinery the scaling dimension of the primary fields, which in this model are just given by normal order exponential function phi. And then once you have your energy and you know that at the classical level, this is what we want to do, ignore any normal ordering issue. So we do this is 4 pi times the original action, and then so the adding such a deformation. The action results in changing the coefficient g. So if you know the formula of scaling dimension, before the formation is g, and is g plus epsilon. So you can compute up to the first order of epsilon how the scaling dimension changes under this equation. Okay? Yes, and together that you'll be absolutely happy with the set for two. This is the major problem of the entire theory. This factor 2. You will see it. Okay, now this was like in fact, a mixture. Something looked quantum because I presented standard expression for fields and energy momentum tensors for scalar. But in defining this rule, I ignored completely the normal ordering issue. So it's like was and we have seen that it still has some impact. But can we do better? Can we consider this deformation of quantum? You have seen that the path integral approach in the TTbar deformation is we use. We mainly Rikard tried this, but it turned out to be more difficult. We really do not know how to go along the line. You can try to write such a determinant of TTbar in a following way, in a similar way as for the just TTbar itself, but you need to make this scaling part of your metric dynamica. You need this. And then, yeah, the integral with the scaling mode, which is sometimes called the UV field, it is. There are different kinds of anomalies we cannot control. Okay, so not really. This way seems to be difficult. We don't know how to go along it. Well, this is one of the problems. The action certainly no longer quadratic. But let me remind you, we have a general form how to compute a deformation of the differential function. And we expect, or at least we assume, that in the correct application of this deformation, the deformity should still be a conformal theory, right? So let us forget for a moment about action functions, defining theory, using them, and let us remind ourselves what we actually need if we want to say that we discuss a two-dimensional conformal field. Okay, so there are several points I think work well. We need to know a central charge, the theory. Well, we have to know how the Hilbert space decomposes into representations of the universal algebra, which means that we need to know the spectra or the scaling dimension of the primary fields we have in the theory. Next, once we have a Hilbert space, we can describe the Hilbert space. We can classify the fields that we have in the theory, local ones. We need to know how two fields merge into the third one. Not only the fusion rules, but we also need to know the coefficients. Ferko coefficient, two-fold relation. This is what we need to know. And once we have the structure, somebody gives me spectrum, three-point correlation function, central charge. To know that I do have a CFT in this kind of axiomatic approach, I need to check whether the crossing symmetry or you prefer the bootstrap equation. So if I had some factor, this is I would say a legitimate conformal field theory. Okay, so the approach we're trying to, the route we are trying to follow is we start from some CFT. And we try to see whether we can compute deformations of the parameters that I have just listed. Scaling dimension, central charge, and charge, 3 points. Okay. Let comes out first for any two-dimensional conformal field theory. And in fact, let me tell you one thing. We are not thinking about theory. Why? Because we are speaking about infinitesimal deformations. In minimal models, you have a discrete set of weights, and it's unlikely that you can do starting from just like this. Once again, why is it unlikely? You know, of course, why in minimal models such a discrete structure appears, because we are just dealing with the general representations. But if I'm starting with general representation and just slightly change the weight, I'm out of the general representation. I'm in generic irreducible representation. So the minimal models would be tricky in this way. So in fact, what I do have in mind is that theory has continuous spectral scaling dimensions and is not a scalar theory and does not have any symmetry behind the pure conformal symmetry. Since there's only one such a thing. Is there a limit? But there is a theory which satisfies all the assumptions. And I'm going to comment at some point that this is not necessarily just a real thing. We can do more, but this is a very convenient starting point. So say, yes, we do have a theory with continuous spectrum of conformal weights, so we can define them. And we know a lot about this theory. Now,
So you're saying that this deformation cannot be universal, unlike the original. You can only apply it in various
I don't know if there's information in the first one. Only is that the recipe we are applying only be applied if you start first. If you the minimum are not understood, then scalar field, well, larger number of scalars, any additional symmetry. So we started from the view, but I don't think whether we should not discuss at some point that was in them, some concept. Okay. The point is that if I'm just starting with a finite set of Bernoulli representations, then I do. But then again, I can answer yes, but you can, if you work hard enough, reconstruct the minimum of this one.
But if you could do this for any CFT, that would imply that all CFTs are part of a line. I mean, it can be. There was part of a one parameter family.
No, I think one can view it as a way that if you are interested specifically in the general representation, you can approach such a theory something from general representation going to general points. So I don't know how limited.
But cannot be universal, right? Because we know that there are CFTs that do not meet marginal deformations.
There are CFTs, right?
There are CFTs, 2D CFTs that do not meet marginal deformations. So
Certainly, because I mean, this is exactly the problem. If you start from a set, we have just discrete set of conformal weights, cannot be deformed, no? Because it's discrete. So but also it depends on the way you define the word universe. Okay?
Okay, for instance, for the TTbar, there is this, you have the TT deformation, then you can use point splitting and define, you will find that there is a local operator associated to the deformation. So in this root TTbar, I do not know if you can apply point splitting and then also find that the associated deformation does have define an operator in the quantum theory. Following point splitting, then that would be the way to say the deformation is universal. But because we have CFTs that do not admit the marginal deformation, then I would say it's not universal.
But this strongly depends on your definition of universe. If you define it, can it be applied to anything except not? If you say, can it be applied only to a single thing? I don't think so.
You have to put the extra assumptions, I suppose, in order to
I assume that I'm dealing with a continuous spectrum of the Villas-Serre. This is what I do, okay? And I have no hope that this is as universal as the TTbar definition.
So by universal, you mean generic?
Okay.
So by universal, you mean generic?
And if I am to specify the assumptions I'm making, we have a continuous spectrum of conformal weights. But I mean, this is just initial work. So what comes out of it is not yet decided. Okay. So, but I assume this continuous spectrum of conformal weights. It's whether I assume this is the standard probability, right, in CFT. And with two slides with some small technical points. First, this term can be written as an action of the operator I have here, only z minus delta zeta. So in fact, I can rewrite this term as a single differential operator on the expense of introducing some factor in the middle. Now, this means that I can write down my word identities and the sum of such two operators acting in functions which are unique. Okay? And then I can compute the nth power of normal order energy sign such an operator as an action of nth time of such an operator on my correlation function multiplied by this explicit factor, and then you can see that with the simple quadratic transformation, you can just reach them as the nth power of the derivative. Why do we know this? Well, because in the next step, we want to compute such an exponential. And if every term in this expansion, I mean, if the action of t is just given by a exponential, then, and I'm really thankful, my friend for this expansion, this is just a sheet of it. You know, root function acts, so you can learn that. Of course, you need to be careful concerning phases, but you can. You can be on the negative, around the negative real axis, and to the right of W, you can fix the phases of these, and then start with the line, which makes sense. So this will be defined really properly. Wow, and now you apply something like a manifold problem. If it was just an ordinary, this is just a number identity, but we can try to define the power of the it's not a key kernel. I prefer to write the gamma as an integral around negative real axis. I do not know how you teach the students the gamma function, but I prefer this way of defining one of the gamma, because then it's analytic for all the arguments of gamma. You can clearly see there are zeros. So the gamma has zeros and has poles and no zeros. Anyway, this is the way you can analytically continue the gamma function, and also analytically continue this integral for whatever value of alpha you have in mind. So we try to define our TTbar information exactly by saying, okay, let us assume that we chose such values of W1, W2, that we can write down this as a purely real expression. And there is regions. And you can start from imagine from the negative real axis. And this is real. The complex conjugate is also real, so you know where you are. And when you analytically calculate some, you do have control over the phases. This may require more careful discussion, but I hope it's not senseless. Okay, we have a function. Now you need to multiply with something, integrate over S and obtain some result. Well, the computation of the analytic form of this integral seems to be not quite easy. We do not know how to compute this integral analytically, but this is just this. I'm sorry. Comment you can about phases. Anyway, even if you cannot compute this analytically, you can find, I think, a well-defined procedure of expansion in one order, the parameter in this case. We still have an ongoing discussion how to properly compute this integral. For instance, this is in fact expanding the function under the interval 1, 0, and you obtain something which is really sensitive. Then you somehow lose the information which is outside of the region of convergence of the series you apply. But we know it's quite easy to see that all these contributions are submitted. You have here some well, leading term delta, and this is like if you have a function with Ferko minimal, right? You can do analytic, you can do the 7-point expansion around all each point, but some will be leading, some will be subleading, so this is like subleading. So like expansion around the leading side. Show this one. Okay. So we can do this. And for instance, we can then compute the integral using any standard regularization because this integral is vague. But this is expected. Right? If you have this type of integral is conformal to theory, and since there is no masking, you do not have the fall off at the infinite singularity exponential, so you expect some divergences. You need to regulate them and then interpret what you get, and you can, for instance, compute that in the leading term what we get some normalization, which depends on the regular regulator. And you get some which is proportional to W2. This is the dependence without thing, and you can interpret this. You can interpret this precisely as a change of the spatial energy. Okay. This is the exact result of the integral. You know that you can compute this. In this type of regularization, you can like so in the first order, on the one of the delta expansion is normalization constant. This is low, and I already told you. So we want 4. So the hound for missing 2 is ongoing. Good. It's funny because we have an expansion one over delta. You do not have to combine yourself to the normal functions. It can be done with patience and mathematical, whatever order you would like to. 4th, then it comes to. But you can do this. It's clear from this expansion, from the formal expansion, you can compute any order corrections. So for the first correction, just get a change from delta to delta minus 1/2, this is 1/4 x 1, and some finite change in this. And the next order, another correction, and we have some ideas, kind of physical idea, which if maybe we work on it a bit, maybe it will stay as it is, but it's likely that we can compute the series and we sum it analytically, and then the result is something like gamma function of delta half plus 1/2 divided by gamma function. Remember, this is still just an infinitesimal deformation in parameter epsilon. But it's likely we can compute the entire contribution coming from this leading dominating cell point analytic. And if you have analytically know how your scaling dependent and changing the epsilon, you can integrate. So I did not write for you the result of this integral, but this is my integral of a logarithmic function of the ratio of numbers. So elementary function, every kid in kindergarten knows properties for it. Good. So the leading term, I show likely, and the word likely refers to this missing term. It really is out of the scalar field. Also, we seem to understand why you get this change of normalization of the field. So this seems to be okay. Now, this is what I told you a second ago. For the delta, it's probably that we can resound it and get a closed analytic formula. Now the things that I decided not to show you on transparency with every computation, we also can conclude not that explicitly the deformation. So we seem to know how the dimension flows. We seem to know how three-point function flows. What about the central charge of the universal algebra? Okay. Please notice that in our definition of the root of TTbar, we have separated this root of TTbar onto the product of root of T and root of T-bar. So if I have this compute my prescription of computing my exponential, whatever this is. So, of course, if this is to be a product of T, this is it. And then the deformation T with itself will give me, well, the correlation function of those two gives you a central charge of time. So in these vanishes, we can probably say that the central charge steps in time to it. So this is a nice but also fun information. Number of degrees of freedom is left unchanged by this flow. Not unreasonable. But if we have this, we can test at least a class. We can go farther because there exists closed formulae for the expansion of conformal blocks with respect to this parameter. You can go as far as you want. In some of my papers from the past, we have like 10 some terms in the recursive expansion in the forms of the entity. This can be done with that. So, thank you.
So please feel free to ask any questions or comments.
So you don't know yet if it's exactly a Markov dimension.
In a sense?
I mean, you haven't checked, for example, the root structure. You don't know.
No, we haven't checked it.
That.
But we checked that what we checked is a key star of this structure of that you can interpret your deformation as a change of this structure, but you don't go to them. There are no, it's completely true, right? You get some quantities to compute. You get some correlators with the computation. You have to introduce them. So you have to introduce a mass dimension. And if there was some anomaly which would break symmetry, you might have a chance to see such a calculation. When you have to introduce a parameter which breaks symmetry, After doing the calculation, we are still in city. We do not know whether this precise formula defines for you a new conformal theory, in the sense that we haven't checked the booster. But yes, it's okay. This is, as I told you, an ongoing one. When we check the booster equations, yes, that is certainly the trivial archive function. Ongoing.
Are you hoping that if you, instead of expanding the integral that you have in powers of 1 over delta, if you computed it analytically somehow, that you would fix this factor of 1/2?
No, this is not this source. At least one. The point is, the function, perhaps I can write. This will be speculations, let me say this. Okay, this is the function. This is the integral of the. Then, in the calculations, we do expand on 0. You can clearly see that you can only have a finite range of energies. Okay. So, of course, you can what you can do, you can divide your interval to pieces such that every piece you will have a convergent expansion. But analytically, computing such an integral seems to be hard. I do not know any. It's really complicated. Even if you just try to see what is the analytic structure of this, wow, it's hard. So I don't know if we have any chance to confuse it. But if you divide this line into these pieces, you have different convergent expansions. For instance, it's quite easy to expand infinity. First of all, as with any 7-point expansion, we have this exponential, right? So I told you the exponential obtained from any other term than 0 is subleading, subdominant. So you cannot obtain the same. Moreover, this is something we're discussing today, the dependent on the side parameters, they are weird. But this may address, this may be related to this issue raised at the beginning. Whatever local, I think such a deformation, such a crazy operator is likely to move you to something which cannot be described by a Lagrangian with finite neighbors. So it's likely to give you something non-local. And maybe this is a kind of a window into what this locality in this respect, non-locality meaning. And because the leading exponential term is different. I suspect rather maybe we have some misunderstanding on how to precisely relate this classical computation shifting G to this computational variation of the relation function.
What is the big parameter in the set point approximation? So usually when you use the set point approximation, there is a big parameter. For instance, in the quantitative ratio 1 over h bar. So
I mean, there is one term which is exponential delta, has delta in the exponential, and the rest
so
is
the delta is the big one.
Yes, the delta is big one. This is in the limit of large delta. So the expansion is 1 over delta in this parameter, and there's one dominating term which has a delta in the exponential. I don't know if I can present it that way, but I mean, there is a delta, and we just right there's a delta that is a log on the rest, and the value at 0 gives you this exponential. Jesus. No, 60 minutes because it's not a fast 5 past. Oh, really?
Yeah. Have any other questions?
So what is known about marginal deformations of the Israel theory? You consider the Israel theory? Is there something known? Is there some natural candidate or what the operator would be?
people will not do this. I don't think this is relevant. I didn't look into what is knowledge about the local deformation here. But if you consider this deformation, you always have the local.
It could end up being equivalent to the nominal.
I don't think so. I mean, it would be very. Because it's almost sure that whatever you get, you can describe as a local action. And we do not know what. The one thing that we seem to see becomes weird is the contribution from the other parts of the they behave strangely. But I do not have enough knowledge at the moment to somehow pinpoint what would be the signature of something new. What is right? But I didn't look into the information of what like this, because this is something else. And I don't think that. Okay, at some point, of course, this is. Thank you for the question. This is a very good remark. Something you need to really know the always, which is relevant. Otherwise, you make it full out of yourself. Yes. So thank you.
So is any part of the calculation into the value of C? I mean, the central charge, other than use constant?
So we never had to use it.
Never had to use.
No, I mean, we will need to use the value of C in the bootstrap equation, of course, because then all the objects C themselves and the conformal blocks they do depend on C. Yeah, this is in fact. We will be doing this calculation in the so-called classical way. You take both C and the scaling dimensions to be all large, but still C remains as a point.
And the TTbar deformation of label theory is something that is known.
Of this of the root theory?
Yeah, not root, but just TTbar.
You don't want it?
No, I don't think
But you know,
doesn't give you a conformal.
But immediately make it non-conformal. So
It's not something people are interested in. So
degree is important as a conformal thing, right? Because you just have the direction infinity. Else. And that's why it's interesting. Difficult starting point. So you don't really expect a lot. Let me tell you one last story. I had a professor when I was young, back in 1001. So he said that there are 3 types of lecturers: bad one, you know, bad one, and good one. Those who speak clearly, explain everything, interesting, and they're very good one. Those who finish on time, in time. I always try to be a very good lecturer.
okay, so if you have no further questions, let's thank Leszek once again.
Thank you. You know how difficult it is for 1 hour to hide your belly?
You can far away from the camera. So.
Yeah, that's great, but you have seen me.
We will do some full edit.